let's get started. Again, just putting things in perspective, Professor Cohn talked about how in a big engineering design project you work through the various stages of, and the first stage is phase A, where you come up with the basic concepts. And I think the level of detail of the system and subsystem lectures that he's giving last lecture and today, we could sort of look at as being on the kind of the phase A level to show the basic feasibility and the overall structure. Those of you from AeroAstro have certainly been familiar with our approach to systems engineering, which we call CDIO. Someone from AeroAstro can tell me the C is conceive, design, implement, which actually means manufacture and test, and operate. So we're kind of dealing in these first few lectures, and this could be looked at as phase A, and then the design, the detailed design, that's your phase B. That ends with the critical design review, after which, in principle, you're supposed to be ready to cut hardware. And then you get into the phase CD, where you actually build and test, and then, of course, we operate. My sort of background, the way I got into engineering, and I probably should have mentioned this at the beginning as sort of truth in advertising, is I was never trained as an engineer, unlike Professor Cohn. I was actually trained as an astrophysicist, but when I went to NASA, I spent so much time working with all the technical systems and interacting with the engineers and the people who use them that I learned certainly a lot about the way these systems are designed and particularly operated. So my approach to a lot of these engineering situations is very much from an operator's point of view, and I'll try to emphasize that as we go along. It's very important right from the beginning of the design, I think, that you think about how you're going to operate the system. We have had too many examples that I've come across, and many people who have to actually operate systems where you build something without really thinking of how the system is going to be maintained and taken care of. One of the things that we have been doing for the last few years is to take a group of undergraduates down to the Kennedy Space Center every January interim activities period and have them spend a couple of weeks with the engineers and technicians who have to maintain and operate the shuttle system. And they hear lots of stories from these the engineers and particularly from the technicians who say, boy, I'd like to have a chance to talk to the person who designed this little system. You know, I have to get my hand all the way around, and it takes 5 hours to turn the bolt, or something more fundamental. And we'll probably discuss this when we talk about the main engines. The fact that originally the main engines were supposed to be reusable without being taken out of the shuttle so that you could cycle them many times. Well, it turns out that in order to get sufficient confidence that the engines are ready to fly, we really do have to take them out after every flight, and they're extensively bore scoped, and you look inside. But some of the engineers in the main engine shop pointed out that for instance, if certain diagnostic test equipment had been built into the engine so that you could have taken data as the engines were shutting down over and above the data that we actually get, possibly we would have been able to reduce considerably the maintenance on those engines. So again, this was the shuttle was the first time we had really tried to design reusability into a space vehicle and engines, and we've learned an awful lot. So I think it's very important when we discuss the systems in the course of the term that we don't just look at the detailed design, but we also consider the operations. That's very important. Okay, so in that spirit, Professor Cohn is going to continue his introduction to the shuttle systems, and Aaron, I'll turn it over to you.
Okay, thank you. Okay, yes, as Professor Hoffman said, I'm really giving you what I would call a technical management overview because when we talk about structures on the 22nd, Mr. Moser is going to come and talk about structures, and he's really going to go into the details, how the loads were calculated, how the stresses were calculated, how Nastran was used, how we came up with the basic structure. But I'm just going to really give you a sort of a overview on it. And I think it's interesting to note that the structures may be a very good system to look at for your project because it weighs a lot. We certainly didn't have all the tools that you have today, tools for calculations today, to make it a more efficient structure. The materials are a lot different. But basically, this structure, if you start at the front of it, the crew cabin, which I showed you a little bit about being made, it's a welded configuration, and the forward fuselage are basically an aluminum skin stringer structure. Very basic aluminum. If you go back down through the mid-fuselage, which is the large part there, the mid-fuselage is again a skin stringer. Interestingly enough, the forward fuselage and the crew cabin were made by Rockwell International in Downey. The mid-fuselage was made by General Dynamics in San Diego. So we had various people putting the structure parts together. The wings were made by Grumman. So we had this vehicle being built all over the country, coming to Palmdale, California for assembly. So the aft thrust structure was built by Rockwell. The vertical tail, I believe, was built by Fairchild on Long Island. Some of these places don't exist anymore. But then you go back to the vertical tail. Again, it's aluminum machined skins with honeycomb. The aft fuselage, as you can see, is very complicated. It's got all the plumbing, all the wiring, all the auxiliary power unit. So it is a maze of plumbing and wiring. You could get lost in there and never find you again. But it is a maze of wiring and plumbing, and it's made basically of aluminum. But a lot of the support structure are boron aluminum thrust structure panels with graphite epoxy skin panels. And then the payload bay doors, which was our innovative material going into large composites. We used graphite epoxy. That was the first time that really a large composite structure was used in a vehicle. Now it's used quite commonly in the Air Force and a lot of places, but graphite epoxy was the panels we used, and that saved a lot of weight. One of the problems we had, though, is when we built these panels, we found we got moisture trapped in it. And of course, the moisture, when you go and heat it up, coming back, it would pop the panels off. So we had to, on the pad, we had to go in and drill little holes in these panels to be sure we could get the moisture to escape. So those are things you learn when you do new technologies. But as I said, Mr. Moser is going to go through a very detailed explanation of this. This may be something you want to consider because there could be a real innovative way of reducing the weight and making the vehicle more robust. So I suggest you think about that for the structure. Now I'm going to go into talk a little bit about guidance, navigation, and control. And some people asked me yesterday where they could find some information on it. And actually, in those orange or yellow books, I forgot what color they are, but that we showed you, they're on hold in the library, have a very detailed analysis and discussion of how the guidance, navigation, and control system was formulated. And it's probably as good as you're going to find. It was very early in the program. It's different than it is, a little bit different than it is today, but it's a very good description of the redundant computer set, the operational fail-safe system. So I think you could really get a lot out of going through that book. Now this chart...
I should just say, there's actually, turns out that we have 2 sets of those books in the library, and they're on reserve, so you can only use them for 2 hours at a time. So there really should not be any problem with everybody in the class having access to those books when you need to go and look at them.
That will probably be the best source, except when Phil Haddis from the Draper Labs comes and talks about the guidance system. I'll talk a little bit more about that. This chart, or this schematic, or whatever you want to call it, was originated by the Johnson Space Center and Rockwell International. It took us many hours, but it basically is the architecture. I'm going to go through it in some detail for the guidance, navigation, and control system. Now, this was the original one. It's a little bit different today, and I'll explain the differences that we have. But this was basically the guidance, navigation, and control system main architecture. And you can see on the left side is what I would call sensors. And first, in a very simplistic terms, some of you are experts in guidance, navigation, control, but guidance, navigation, and control, navigation is actually determining where you are, guidance is getting to where you want to go, and control is controlling the vehicle and its stability and its characteristics around the center of gravity. So that's basically control. So this is for the total guidance, navigation, control system. Interestingly enough, the contractor for this was IBM Federal Systems Division. We used their computer, and they did the software. Much of the hardware was designed and built by other contractors, and Rockwell International basically did the integration. And they did the integration on a system called the Shuttle Avionics Integration Laboratory. It was basically a vehicle that was in the laboratory that had all the electronics, the cockpit, and everything in it. It simulated the actuators. The hydraulic system was simulated, and the engines were simulated, but basically all the hardware and software was in the Shuttle Avionics Integration Laboratory. I imagine you spent some time.
We actually had two. We had one in Houston, and there was one out at Rockwell. And when Professor Cohn says that it was a vehicle, you have to appreciate it. It was actually laid out just like the shuttle, so that they had the controllers, which were in the aft end, like in the engine compartment, were 100 feet away from the crew cabin and the computers, and all the lines, the data and power lines were laid out as closely as possible to physically duplicate the layout in the shuttle, because there was concern about the timing of signals going back and forth, and they wanted to run the simulation as accurately as possible. They had, and then of course you have to have a set of simulation computers to try to determine the environment that the shuttle would be flying in, and so that it could make the inputs to the rate gyros and the other parts of the measurement units to try to duplicate the flight regime.
And here's a explanation of the alphabet soup of all the systems, subsystem components. But on this side, you see really the sensors. That's the information that you need to do your navigation part of it. And then, of course, that information then is sent to the computer through a multiplexer, demultiplexer, an MDM, which basically is an analog to digital converter, a digital to analog converter. The computer does its computations and then sends it to the effectors, which actually change whether it's the RCS, reaction control system, whether it's the orbital maneuvering system, whether it's the aero surfaces, the SRB actuators, the solid rocket booster actuators, the main propulsion system actuators. So that's really how you get sensors, computation, and effectors. Let me talk a little bit about one sensor, which probably is many of you can relate to, and that's the IMU, or the Inertial Measurement Unit. Draper Labs is famous for its inertial measurement units. I worked with Draper Labs, or MIT Instrumentation Lab, on Apollo, and we had the original inertial measurement unit developed by the MIT Instrumentation Lab in that vehicle. The inertial measurement unit has gyros on it to determine angles, and it has accelerometers on it. And it is aligned with the star tracker. It's basically a stable platform, and it's aligned with the star tracker to get a reference system in inertial space. And when you make a maneuver, you get acceleration, and you send it to the computer, and you integrate it once, you get velocity, you integrate it twice, you get position. And it's also used during powered flight, and it's used during entry. But that then goes to the computer. So the inertial measurement unit is very critical. Just to give you an example, though, here you have three of them. These show you have three of them. and you got 4 computers. I'm going to talk about the computers in a minute. You have 3 of them. You had to recognize when we went to the moon on Apollo, we had 1 IMU and 1 computer in the command and service module. And we had 1 IMU and 1 computer in the lunar module, except we did have a backup system called a strap-down system. We did have, one was built by, primary system was Draper Labs, MIT, and the backup system was TRW. So we had 2 different contractors. And then you have rate gyros and accelerometer assemblies, primarily for ascent, for the stability of the bending of the vehicle. Here's the air data transducers that we talked about yesterday for entry. Then you have the microwave landing system, the tactical navigation, radar altimeter, rendezvous radar. These are all sensors you use during various phases of the mission, which again go through the MDMs or multiplexer demultiplexers to the computers, and then to the effectors, which change your position and velocity as need be. Let me talk about the computers for a moment. You see 4 computers. That was the real test of this system. We had 4 computers that were synchronized. This vehicle, as we talked about yesterday, we decided to make it, for your aerodynamicist, we decided to make it statically unstable. We saved a lot of weight. By that I mean a regular airplane, a normal airplane that's stable, when you get a disturbance, it'll come back, it'll still come back to it without any augmentation, it'll come back to its original position. With this vehicle, if you get a disturbance, it'll diverge. So you had to continually have augmentation. So you had to have a operational fail-safe system. And that's why you have 4 computers. It's fail operational, fail safe. You can lose 1 computer and you're fail operational, you use another computer. That means you got two left and you're fail safe and you come home. So, so that's what it is. Now, the real concern about it is these computers are synchronized. They essentially communicate with each other 440 times a second. I'm recalling a lot of this from memory, but 440 times per second, and they actually vote on each other to a simplistic form of terminology. And if one computer is out, it votes it out, another computer takes over. Basically, that's but the concern we had was that in doing this, we could have a generic failure and lose all computers, or we could have what we'd call a two-on-two split. And these would be sort of diabolical errors which would cause the vehicle to fail. So we decided, after this was made, to put in a backup flight system, a backup computer, a 5th computer. Now, it turns out there was an argument there. Should we have the 5th computer a different computer and different people, or should we have a same computer with different people? And we argued long and hard on how to do it. And we had a lot of experience with the Draper Labs. The Draper Labs just did an outstanding job, or the MIT Instrumentation Lab just did an outstanding job on the Apollo vehicle, both on the command and service module and the lunar module. So we went to the MIT Instrumentation Lab, Draper Labs, and asked them to actually take the same computer but put it outside the loop. It's not part of the redundant set. It's outside the loop. It gets all the, I didn't show the schematic right, because it gets all the same information that the other computers get, but it then can take over if the primary system fails. Now, Phil Haddis did this work for the Draper Labs for NASA in this backup system. He's going to give you a lecture. So he's very good to lecture on this total system. He can tell you about the total system. But we thought we'd put the backup flight system in just for a short period of time to give us confidence on the primary system, but it turns out that we started putting things in it that now we need it, so we could not take it out. So it's really part of the major system. So that is a very different part of the system today. I don't think we ever really had a diabolical problem in flight. I think we did have one in the Shuttle Avionics Integration Laboratory one time where we had a 2-on-2 split. But when we did the approach and landing test, where we had the orbiter on top of the 747, and we separated the orbiter and landed, I remember that first flight, I was sitting in the control station at Edwards Air Force Base. At that time, I smoked a pipe. And when we separated, a big X came across the screen because we lost the first computer. But I guess the shock actually broke a solder joint in the computer. The pyrotechnic shock from separating actually broke the first computer, so we had to go to the second computer. I bit my pipe in two, but it did prove that the redundant set did work because it took over and landed well. So we had a very successful in-flight test, not planned, but it turned out to be a very successful in-flight test. Now this, when you make the computations, you get the information on position that the computer computes. It sends it to the effectors. The effectors may be during entry, during the high part of entry, may be to the reaction control system, the forward RCS system, or to the aft, or it could be to the OMS system if you're trying to make a maneuver. Or when you get down lower in the surface, lower in the atmosphere, it could be the aerosurface actuators. And then during ascent, it's to the TVC for the solid rocket boosters or the main propulsion system. So those are the effectors. The flight control system is a very interesting system because for entry, because as you can envision, early in the flight, early in the entry, you don't have any aerodynamics, so your aerosurfaces aren't of any value to you, and you use the reaction control system. But as you get farther into the atmosphere, the loads become so high that the reaction control system becomes ineffective, and then you have to use the aerosurfaces. So it's a blended system, and the system has to know when to handle the aerosurfaces versus the reaction control system. And of course, then you also have displays to the crew, and actually information that the crew can use to make certain decisions. So that basically is the guidance and navigation and control system. There's one additional change that I don't have on this chart, is that they have incorporated the global positioning system in the shuttle. The GPS is now part of the system. It took a long time to do it because I remember it wasn't done when I left, and I guess you said it was. Were you still there when it was implemented?
Yeah, they started. They did put it in.
And on GPS, you can essentially get position. If you could get attitude, then theoretically you could eliminate the inertial measurement unit. So, and I don't think they do it that way, but theoretically, the GPS, for you looking at the guidance system change, you ought to. This again becomes a very interesting system to look at. Would you do it different today? Would you do it? For example, these computers. This is the computer was used as I can't remember all the characteristics of it, but it's basically the IBM 4-Pi computer, which is a very old computer. It's probably made before many of you were using computers. But, huh?
It was an old AP101, which I think was a design from the early 70s.
Yeah, it is the early 70s, yeah. So this would be a very neat system to take a look at for your system. Not only that, you probably could get a lot of support from Draper Labs and that type of thing. So it'd really be a good system to take a look at. And I'm sure you can make a lot of improvements. Those improvements could theoretically be used on the new CEV, the Crew Exploration Vehicle. So I think it would lend a lot of merit to you, you very smart people, to take a look at the guidance, navigation, and control system. Yes, sir?
Transducers, was there more than just pitot tubes and static ports, or?
That's all it was, I believe. I think that's was, yeah. We had a lot of problems with those. I think it's just very old technology. Yes. Yes. Yes.
How'd you get position?
You got told me about it. I'm sorry.
I was going to ask how you got position information before GPS.
Position? Well, it's. Don't know exactly, but it's got what, 13 satellites going around. Yeah. Can you?
Well, there's two ways. Yeah, I mean the desire for GPS, of course, was to give the shuttle autonomous navigation capability. The shuttle, with the star trackers and the IMUs, it has the autonomous ability to determine its attitude, but it doesn't know where it is because the inertial measurement units drift over time. And so you need to be able to update the state vectors. Originally, this was done by the only way you could do it was radar tracking from the ground. You would track it, you'd get a state vector, you'd uplink the state vector, and then the shuttle would know where it was, and then periodically you have to update it because of IMU drift. once we got the tracking and data relay satellite system installed, you do have a certain you do get navigational information by the Doppler navigation
Right.
from the signals coming back and forth through TDRS, but it was generally calculated on the ground. So it was not really until the advent of GPS that that we got autonomous capability. You need it for things like, I mean, if you're going to deploy a satellite, for instance, you need to know your position pretty accurately, because the satellite is going to take that position and has to do its burn accordingly. And obviously for your reentry burn or for rendezvous, it's critical that you know your position. When you're doing a rendezvous, the shuttle does have a rendezvous radar.
Yeah.
I don't know if we'll deal with that in detail. So once you get close enough to the object that you're rendezvousing with, such that you can get it either with your radar, or they actually use the star trackers to optically track the object, then you can start getting your relative position with respect to the object, even though you may not know your absolute position. And so from that point of view, the shuttle gets a certain degree of autonomy. Maybe I'll just say one other thing about the computers, because, I mean, people are amazed at how primitive the shuttle computers are.
That's right.
But like I say, the original idea and the concepts that we talked about, this was going to be, you know, an airplane-like vehicle, and originally they wanted to use some off-the-shelf hardware.
That's
and
right.
Of course, the AP101s, as they finally used them, were not off-the-shelf. But you know, these original computers had 128K of memory. And the memory they used, probably, I don't know if any of you have read back in the history of computing where they actually had the little magnetic ring cores with the wires going through. I mean, this was really old stuff. And they did finally replace that with a solid-state memory with a whopping 256K. And again, probably none of you have dealt with overlay technology, but back when I was a graduate student and we were using computers to do complex astrophysical calculations, sometimes you would have a program that was too big for the computer memory. So you'd have the whole program on a tape recorder, and you'd segment it into what they would call overlays, and then you would load it one part at a time, and it would do its calculations, and then you would stop and load the next batch of software. Well, that's the way we have to run a mission. The computers cannot hold enough software to do ascent, orbit, and entry. There's 3 segments of flight software. You start the mission with the ascent software loaded. Then when you get up into orbit, you do what they call a major mode transition, where you basically, you know, you punch a button and everything goes blank, and you sort of sit there saying, hope this is going to load properly, and the tape recorder chunks away, and then it loads the orbiter part, the orbit part, and the same thing when you're getting ready for entry. Now the backup system, they decided that they didn't want to take that risk, that if something went wrong in a major way, they wanted the whole flight software on the backup system, and that meant it had to be scrubbed. So the backup system is capable of flying the shuttle and getting it home safely, but there are a lot of capabilities which the main computer system can do, which the backup system can't do just because they're limited to the amount of software. The one other thing I'll say is, you know, putting together this redundant set of 4 computers, because as Professor Cohn said, the shuttle will not fly without the computers. So, I mean, it is absolutely flight critical. So, you know, hundreds of times a second, every computer is looking at the data from all the other computers, and they're all voting. And so you have this matrix, just to make sure you understand the way the system works. If computer number 1 sees a problem with computer number 3, it's likely that computer 3 is also going to see a problem with computer 1, because they're doing something different. But if computer number 2 sees a problem with computer 3, and computer 3 sees a problem with computer 2, and computer 4 sees a problem with computer 3, now you've got a 3-to-1 vote, and so computer 3 will recognize that it is the problem, and it will take itself out of the set. And that's what happened with the, well, in that case, the computer actually shut down. I remember that big X. And
I bit my pipe into.
And at the same time, all of this information has to go back and forth to the backup computer, because if you're ever going to engage the backup
computer, be ready to go.
It has to be ready to go at a split second's notice. And you know, the big question is, suppose you get, there are situations where you can get a 2-on-2 split, and you know, when we run through the simulations to learn how to work this, actually learning the ins and outs of how to work the computer system is probably one of the biggest training loads.
The astronauts become more knowledgeable than the designers.
Yeah,
they actually, that's their lifeblood.
Yeah.
If there's this danger of a two-to-two vote, was it ever thought about to have 5 computers?
Well, that's why we put the backup system in.
So, oh, it's the backup.
Yeah, the backup system. That was really why we put the backup system in, because it did a little bit more too. It was programmed by different people, even though it used the same computer. It was actually programmed and formulated by different people. So that was one way of saying take away any, you might say, systematic errors that were in the redundant set.
In other words, they kept the same software requirements document, but it was the actual coding was done by Draper rather than by IBM, because that was the other problem. You know, suppose all the 4 computers are doing the same thing, but there was an error in the code which never turned out, so that something starts to diverge, and you know, what's your protection against that?
There's a big argument in doing that. The real argument says, should you really have this a different computer? Should you really just do everything differently? Just have a different computer, different everything? And of course, there's advantages to that and there's disadvantages to that. So we settled on this as something to do. I think there was another question. Was there a question back there? Yes.
Yeah.
I think. Yeah.
I was wondering, you said this was the first fly-by-wire system. I was wondering what competing ideas there were besides having maybe a 4-computer voting system.
Well, with fly-by-wire means that when you put an input into the control system, whether you do it manually or whether the computer does it, nevertheless, it's ultimately your command just goes into the computer. You know, you put the stick to the left, saying I want to do a left bank. All you're doing is telling the computer you want to do a left bank, and now the computer has to figure out what's my navigation state, where am I if I'm coming down through the atmosphere, what's my altitude, what's the air pressure, what's my Mach number, and then it's programmed with aerodynamic control laws. This is one of the big challenges because, as I mentioned the other day, you hit the top of the atmosphere at Mach 25, you do your initial control with the RCS. As the dynamic pressure starts to increase, you know, first the ailerons, the roll becomes active at about I think 10 pounds per square inch, something like that. Is you blend the roll control into your aero surfaces at about 20. I think it's pounds per square inch. You can do the pitch control, but because the shuttle is coming in at a 40-degree angle, the vertical stabilizer is pretty much shadowed. So for yaw control, you actually have to keep using the RCS all the way down to about Mach 1 when the shuttle finally pitches down and the vertical stabilizer now has some effectivity.
All that comes, the computer calculates all that, this information, and it comes to use the effectors. It comes to the effectors, and that's what you do the control laws on that.
And the problem is that the flight control laws, which the computer has to use in order to control the air surfaces in the RCS, are not constant on your way down. I mean, the flight control laws at Mach 15 are very different from at Mach 5. And there's a part of the flight regime, for instance, where if you want to do a left bank, you actually have to start by commanding a right yaw, and then the aerodynamic, the cross-coupling terms in the aerodynamics actually causes you to go in the other direction. It gets very complex, and the flight control system is continually changing as the entry progresses. And so the idea that, you know, maybe you should have a direct backup link between the pilot's inputs and the aero control surfaces, although, you know, it might give you a warm, fuzzy feeling, you could not fly the shuttle directly, because to be able to take into account these changing control laws on the way down, you just can't do it. In fact, the shuttle is uniquely, I mean, unless the shuttle knows where it is, if the navigation state goes bad, the shuttle cannot fly. You could have the runway in sight, but if the shuttle's inertial nav state is wrong, you'll lose control and you can't land. So it's a very complex system from that point of view.
This is a very, very, if you can envision the systems engineering that went into this system, it takes aerodynamics, it takes flight dynamics, it takes electrical signals, it takes guidance laws, navigation laws, hardware, software. This is probably the biggest integration job or systems engineering job that you have on it requires everything. It also has to take into consider aerodynamic heating. I'm going to show you that in a minute, because you got to be sure that you don't fly outside the regime that you were designed for aerodynamically. I think you had a question.
Yeah, just real quick, how big are those IMUs? Because you know, nowadays you can get
these well, you know, I don't recall. I do know
it's a box, sort of like a shoe box.
The Apollo IMU was about this big. That was built for the Polaris vehicle. It was one IMU, and it was a 3-gimbal platform. And I remember it was a big issue, but a 3-gimbal platform, you know, has a singularity. So you had to maneuver the Apollo vehicle a certain way so you didn't get the singularity in it. And one of our astronauts, Jim McDivitt, who's quite a famous astronaut, who was a good friend of mine, said he wanted a 4th gimbal. And there was no way we could get an IMU in that day and time with the 4th gimbal. So what I did is I gave him a 4th gimbal to carry with him on his flight, a little gimbal system to get a 4th gimbal. But
yeah, we didn't have the gimbal lock problem on the shuttle.
No, you didn't know, because it's 4 gimbal platform. But I remember we went through that with MIT Instrumentation Lab many times, because all you could get at that time, because the IMUs were so big, a 4th gimbal was almost impossible. And McDivitt was a very good astronaut, but he wanted 4 gimbals. In fact, he wound up being my boss. So
before we go on, let me just mention one more thing about the backup system. The backup system actually takes a lot of care and maintenance, and there's a lot of money that goes into that. And this is not a dead issue, because in the design of the CEV, NASA's going to have to make a decision. There were some guidelines which were produced a couple of years ago out of the Johnson Space Center with a lot of astronaut office input about what are the requirements in the future for human space vehicles. And they put in that you should have a backup computer system, because, you know, basically that's the way we did the shuttle.
And that was actually that was an afterthought.
Yeah, and yet now it's being listed as a requirement, and this is now being questioned for the CEV, because it's a huge financial impact, and so we're going to have to deal with these problems all over again. So it's an interesting thing to think about if some of you want to delve a little bit more deeply.
I think this could lead to a very interesting activity for you. Yes, sir.
Have their own sensors, or are they reading the same?
No, they get the same sensors. I just didn't show this very accurately, because I looked at the chart when I had it, and I said, my God, this is the wrong chart. But this was the chart, this was the original chart before the backup system, so I quickly penciled in the backup system, so I remember talking about it. But no, it has the same sensors. It has all the same information.
But again, most of those sensors are redundant.
Yeah, they're redundant sensors.
Not all of them, but most of them.
Yeah. Any one of the 4 computers can be any of these sensors. It's not like sensor 1 is dedicated.
That's right. They're put on, the sensor input is put on a data bus, and they have multiple data buses, like 4 data buses, and each of the computers can read all 4 data buses. I mean, there's just a tremendous amount of redundancy built in.
Yes, go ahead.
Did they ever use the star tracker to update your gyros? It's like
platform? Yeah, they do that. Yes.
There's also a procedure. If you totally lose attitude, then you have to go right back and manually take a star site and orient, and that we've only had to do in the simulator. Never had to do that.
You know, to look at the failure history of this would be very interesting. It's been, I know we lost, in my tenure, I know we lost 1 inertial measurement unit. We lost that 1 computer during the approach and landing test. I don't know what other failures we actually had in this system. I don't know if we ever lost any. The MDMs, this box was made by Sperry at the time in Phoenix, Arizona, and I've visited that many times because that is probably the most complicated electronics box of this whole system other than the computer. It's very, very complicated. Yes, sir.
Computers have developed a lot faster than aeronautics. So why do you still think that it'll be a major expense now?
I don't think it'll be a major expense now. I think, as I recall, and you're absolutely right, NASA does not put a lot of money into development of this technology because other people have done it. It's pretty much so much more sophisticated than we have now. Don't need it. It turns out, though, at one point in time, structures was the most important, most expensive component of a spacecraft. Then, of course, there was propulsion, and then there became avionics and software. And avionics and software for the shuttle is very, very expensive. It's probably one of the most expensive things. I think today, in today's environment, with the technology we have, with in both software and hardware, I think it won't be that expensive anymore. So I think you're right. I think it's very good. That's why I'm saying, in redoing it, you could use new technology and really show how much less it's going to weigh because the IMUs are probably going to be smaller. You could reduce the weight, you could reduce the electric power, and you could reduce the cost. But you're going to have another detailed briefing on this, and I think it's Phil Haddis. I know him very well, and I think he'll do an outstanding job in explaining to you what's happening. Let me just show you briefly, very briefly. We talked a little bit about this yesterday, but here are some of the things that are profiles that the guidance system has to be able to do. It certainly has to take care of launch. It's certainly the abort modes, which are interesting. There is a abort mode that's a return to launch site, and I guess you would use return to launch site primarily for a main engine failure. I guess that's so. If the main engine fails during ascent, you can go to a return to launch site.
Or a total loss of cabin pressurization.
Yeah, something like that. And I guess that's never been tried. And I guess that's probably one of the most difficult maneuvers, most biggest fears the astronauts have if they ever have to come back to return to launch site. But of course, the guidance system's got to be capable to take care of that. Then you have abort once around. Again, when you may have a main engine cut off, your separation, and you abort to once around. Again, I guess that's primarily a main engine problem. And then you have, of course, an abort to orbit. And those are the three abort regimes you have. Yes, sir? Transatlantic, yes. You have transatlantic abort. That's right. You do have transatlantic abort. Yes, thank you.
That actually drives the launch window.
Excuse me?
That actually drives the launch windows.
Yeah, right.
If they don't have clear weather overseas,
Right.
Iran,
That's right.
place like that, they don't launch.
Right. So the guidance system has to take care of all those abort modes. Again, I'm sure Phil will go through this with you, but first stage guidance consists of attitude and throttle schedule as a function of relative velocity. So it's not completely open loop, but it's almost an open loop system. But you do control the thrust vectors of the engine and the solid rocket booster actuators. And it's the key thing, though, where systems engineering comes to play. It has to it's got to get maximum performance, but it's got to be shaped. The angle tack history has to be shaped to control aerodynamic loads, because some of the highest loads you have, and you'll find out when Mosher talks about it, some of the highest loads you have on the structure is during ascent. Control of maximum dynamic pressure, and you have to provide the flight angle at SRB staging to allow recovery of the spent boosters. So these are some of the constraints that you have, and again, this comes out to be a real systems engineering problem. And for entry really becomes a task in itself, because one of the basic problems you have to control is thermal control. The thermal protection system. I should have pointed out on that structural slide that the backface temperature of the tiles have to be at 350 degrees Fahrenheit. Well, the surface temperature may be 15 to 2,000 degrees Fahrenheit. The back face has to be at 350 degrees Fahrenheit, because that's the limit of aluminum. So you've got to control the guidance, the thermal control for guidance is to keep the vehicle within the temperature constraints in the peak heating region. So that's all got to be married together so that the tile system you design keeps the back face temperature to within 350 degrees on the aluminum structure. Then you go into equilibrium glide. Constant bank angle that we were talking about is modulated for drag control, and then the transition guides the vehicle from the high L braking to the lower angle of attack, and then you basically land. So all this has to be tied together for your guidance, navigation, and control system. I have one more system that I'd like to talk about briefly that gives you, you're going to have another very detailed briefing on this. This is the hydraulic system. This ties in together with the other systems we talked about, the flight control system, the guidance system, primary flight control, because the hydraulic system is a 3,000. It's 3 systems. It's 3,000 pounds per square inch system. It's what does it do? It basically is used during ascent and entry to control the thrust vector control of the engines, for the body flap, for the elevons, for the rudder speed brake, the main engine actuators for the main engine, the doors for the external tank separation, main landing gear, nose wheel steering, and so forth, and so braking. So that's what the hydraulic system does. It's if you lose your hydraulic system, you've had a bad day. And there are 3 systems. I do believe is one place where there's a single point failure in the hydraulic system. It's pretty hard to eliminate all single point failures. I believe that. When Henry Pohl talks, he's going to be doing that, very detailed discussion on the hydraulic system. You might ask him that. I don't recall, but he'll tell you whether there is a single point failure in the hydraulic system. And the hydraulic system, this is a schematic of it. I'm not going to go through the details of it because I'm not sure I can explain it. But basically, this is the hydraulic system. It shows how System 1, System 2, System 3 is tied in to the right outboard elevon, the right inboard elevon, and so forth and so on. The main engines, the external tank, and we've never had a loss in the hydraulic system. We did test the hydraulic system in what we call the Flight Control Hydraulics Laboratory at Downey, where we had actually all the hydraulic systems tied together with the computer system, and actually flew the vehicle in what we call this Iron Bird, where we actually had a hydraulic system. And we did have a failure there at one time early in the program. We had a failure where we ruptured, we had a single point failure, we lost all the hydraulic fluid. We had to go back and make a major change to the actuator system, the hydraulic system. One other, yes, sir.
I'm just wondering how the hydraulic system on the shuttle compares to the hydraulic system on
an airplane.
aircraft, yeah.
You know, I'm really not sure I can explain it because I'm not. I think there's not much difference. The only difference, let me tell you that. Let me tell you the only difference. I think the airplanes, and somebody's here more an expert than I am. I think airplanes have 3 hydraulic systems. The shuttle started out with 4 hydraulic systems. We actually started out with 4, but it was so heavy and so complicated we decided to go to 3. And I think I think the airplanes have 3 hydraulic systems, if I'm not mistaken. Does anybody know? I'm not.
I at least know quite a few that have 3. I don't know if all airplanes have.
The big difference in it is that the hydraulic system in the shuttle is powered by what we call an auxiliary power unit, and that's what pressurizes the system. And I think on an airplane it's powered by the turbines of the engine itself. But this system is pressurized by what we call a auxiliary power unit. Auxiliary power unit is a box about this big. It generates 135 horsepower, and it's got a 10-inch turbine wheel, and it goes about 10 to 20,000 RPM, and actually it's fueled by hydrazine, and it essentially pressurizes the system to get you up to 3,000 psi. Again, if this auxiliary power unit doesn't work, they have 3 of them. If this auxiliary power unit doesn't work, it's a bad day. And I think we did have some problems with one of the auxiliary power units one time during ascent. But that's the major difference, I think, because I think we tried to copy pretty much aircraft designs using the same type of hydraulic fluid and everything else. So I think we copied their standard in using it, as I recall, except we're pressurized by the auxiliary power unit. Again, not to belabor the point, you're going to have a very detailed briefing or lecture on the hydraulic system, the auxiliary power unit, and the reaction control system, the OM system, by Henry Pohl. So you'll have more details on this. Again, the hydraulic system might be another interesting thing to take a look at. But I hope what I'm trying to get across to you is how these systems all fit together. You can't do the guidance, navigation, and control without the hydraulic system. You have the aerodynamics, and you have the aerothermodynamics, you got the structures, you got everything that has to fit together. And you can imagine the systems engineering problem associated with trying to put all that together.
Just to remind you a few of the other things that you have to deal with, if you can leave that on.
Excuse me.
When you're working with a space system that also makes it a little bit different from designing for the ground. For instance, you have a fuel tank with the hydrazine or hydrazine in it. You know, this is a generic problem with any liquid tanks. Once you're in weightlessness, how do you get the liquid to flow out? This is actually a fairly traditional, old-fashioned design where they have a diaphragm in the tank, and on one side of the diaphragm you pressurize it with either helium or nitrogen, and that pushes the material. You know, it's basically sort of like squeezing it out of a bag. The problem is that hydrazine is nasty stuff, and in the orbital maneuvering and reaction control systems, they decided that for reusability they didn't want to use diaphragms, and so we'll probably learn more about some of the details, but there's a very elaborate screen mechanism which uses surface tension to collect the material, and just getting liquids out of a tank into where you want to go is something you have to worry about in space. The second problem is a thermal problem. You know, you're not flying through the atmosphere, so you don't have air cooling. So, you know, as you see, you've got the gearbox, you're generating a lot of heat, and you actually, in order to cool, they use water spray boilers. So you essentially, and we actually do this to get rid of heat from the orbiter as well before we open the payload bay doors, which have radiators. While those are closed, it has to be done with a water spray boiler, and so you get rid of all your heat by putting it into a heat exchanger, and you basically shoot liquid water, and of course in a vacuum the water flash evaporates and that takes the heat away. So there are, although you know, in essence the control system is similar to airplanes, there's a lot of special design features that have to be put in because this is a system that has to work in space as well.
That's a very good point. The cooling is one of the biggest differences.
Because this system is so complex and heavy and needs a lot of maintenance and uses hydrazine, which you know, is very nasty stuff, there have at various occasions been studies of could this system be replaced by an electromechanical system, and as motors become more powerful and battery and fuel cell systems are more efficient, I think just about 2 years ago we gave up on the last effort.
But I think
it always turned out to be
too heavy. Too heavy.
To get an electromechanical system which had enough muscle to move these air surfaces around, it just is beyond what we could
But that
do.
might be another good system to take a look at today. It might be another good system. The other thing is this does have you see where it has a speed control and safety for the APU controller. The interesting thing about this turbine wheel, I forget the exact RPM, but it's pretty high. I think it's at least 10 to 20,000 RPM. If this should break off, if this shaft should break, and that it's very hard time to control it in the box. I mean, it'll go right through the box it's in and shear the vehicle. So we've tried everything we know. We put protection around it. We put a lot of margin into the turbine wheel, into the shaft, but that's a very critical thing. And as Professor Hoffman mentioned, there's been many exercises to replace the auxiliary power unit. And I think, again, this would be another good challenge to take a look at seeing what you could do to come up with a different design for the auxiliary power unit. But there'll be other systems that you might want to look at. But I thought I'd just give you a little discussion of some that I personally think are very pertinent that look at. That's what the thermal protection system, the structures, the guidance, navigation, and control, the hydraulic system, including the APU. And these, I think, would be very good systems. Now, you might pick others, but these might be very good ones to look at. Let me wind up my discussion by talking to you what I think you ought to look for in the systems. This is just a very simplistic chart, but this is my way of thinking about what you do when you go about designing something. You need to look at the functions. As we pointed out yesterday, the functions are very important because when we talked about thermal protection system, we looked at the functions of protecting the vehicle, maintaining that back surface temperature to 350 degrees Fahrenheit. We worked that to finite detail. We knew exactly how thick the tiles had to be, what the characteristics had to be, but what did we do? We forgot, oddly enough, that it had to be attached to the vehicle soundly, which is sort of dumb, and you would think, my gosh, they ought to be able to do that, but you're infinitely smarter after you find out your problem. So one thing you ought to do is really understand what functions have to be performed, and you might say that becomes your functional requirements. The whole thing is understanding your requirements. Then you ought to understand what performance is required. In other words, performance requirements. You ought to have a first order of magnitude calculations of what kind of performance requirements you need. A lot of times this is going to have to come from assumptions, talking to people, getting experts involved. But what kind of performance requirements? It's going to have to be iterated, but what kind of performance are you thinking about in this system, whatever the system may be, hydraulic system, thermal protection system, whatever. Then we talk about the three-legged stool, as Professor Hoffman said. We talk about schedule, cost, and I put weight under performance. Because as I told you before, the first thing you're going to wind up in designing a system, that the weight's going to get too high. Then you're going to find out that performance goes down. You have schedule slips. But first thing usually happens that you find out, you wake up one morning and you find out, my gosh, my system weighs a lot more, my subsystem weighs a lot more than they told me I could have. So you ought to understand your weight. And then you need to think about what is the available technology. What's the technology available? As somebody pointed out, you pointed out, today the avionics technology is probably pretty high up on the ladder. And you could probably pick something today right off the shelf. Although in my experience of the 30 years I had in the space program, I never was able to find something that was off the shelf. Space programs just don't usually allow you to take something off the shelf. People told me to go do it, and once I went and did it, we changed everything. But today, in the technology we have in the avionics, you may be able to get a lot of off the shelf. So what technology is available? And then one of the key things, one of the biggest things you have to know are what are the interfaces. You could see the multitude of interfaces that are required for the guidance, navigation, and control system. It takes into consider all the interfaces you could think about. And so you need to think about interfaces, whether they be mechanical, whether they be electrical, whether they be functional. So you need to think about what interfaces are you talking about. And to me, that is some guidelines you need to think about. Of course, then we talk about, as we said, cost and schedule. Usually your cost is going to grow, unfortunately, and usually your schedule is going to slip. And those, what I would call, are career-limiting problems. That's the best way to get fired, is to have your costs go up and your schedule increase. So these are some of my guidelines for things you ought to look for when you try to design your system. I'd be happy to answer any questions for you that you may have. Yes, sir.
Question that you said about taking technology off the shelf, and I'm wondering, I don't think, from what I know, it wasn't really thought of much during the shuttle, but the idea of maybe putting something on the shelf, so to speak, the idea of designing something so that it would have a subsystem or something, so it would have the flexibility to be used in future systems, and where that, do you see what I'm
No, I don't think I quite follow what you're saying.
The idea of, well, you said there wasn't really off-the-shelf technology available then, but maybe there is now. So the idea I'm thinking about is the idea of designing something not so much just for the shuttle in this case, but so that it can be used
for other things. Well, of course, that's a very possible thing to do and be a very good thing to do. But in my experience, and we've tried something like that, but usually this tends to start growing into it. You start to saying, well, what is it really going to cost you to do that? I know when I was project manager, people would come to me with something like that. And I was pretty mean. I used to be a pretty mean guy. I'm not quite as mean as I used to be. But when they come to, that's the first thing I'd ask them is, what about the cost? Because that's what happens. When you start trying to make multiple uses out of something, you usually drive the cost up. And that's what you have to be careful of. It's, yes, sir.
Can I give a quick story on this idea of putting something on the shelf?
Sure.
Over in the Duffy building, there's a spacecraft hanging up in the lobby, and I'm not sure if it has a logo on it or not, but it's the answer I found out 2 years ago as to why Draper Labs got the prime contract for Apollo GNC 3 months after John Kennedy made his 61 announcement. Keep in mind, the 61 satellites were really, really crude. But Doc Draper, with his leadership and vision, decided several years prior to put IRAP money into the following mission: an autonomous, automatic 4-year mission to Mars. Keep in mind, we had not really gotten the hang of launching the low Earth orbit. Send a satellite out that would not require any ground commands. Star trackers, fly by Mars, take pictures, I believe on glass plates, come back. This was a kind of a very far-reaching concept. He decided that to make it happen, he and Aver, they needed to have a very high throughput, very reliable space radiation qualified computer. And that's what they developed on their own money. Because they said, if we don't have that, the mission just can't work. So they didn't build the spacecraft, they built the computer. When John Kennedy made his announcement, Draper Labs was positioned to say, we have key technology here. That was the heart of the Apollo guidance computer.
Well, let me add to that. I feel very strongly that had it not been for the MIT Instrumentation Lab or the Draper Labs and the people they had there, the technology they had there, we wouldn't have gone to the moon when we said we were going to do it. I really feel, I mean, I work very closely with them, and I feel very strongly that the Draper Labs, I keep getting them mixed up. At that time, the MIT Instrumentation Lab was really the one of the prime movers of the whole system. It was really fantastic. So the people working here and can take advantage of that. It'll be very useful for you to do that. Any other questions? Well, I won't be here. I'll be back on the 22nd, and look forward to working with you some more. Oh, sorry. Yes.
Yeah.
Sorry.
Not as much to do with the subsystems, but back to the overall concept of the shuttle. I was wondering why, if you know at all, why the military thought it was important to have the ability to capture a satellite and bring it back. Was it because satellites were so expensive at the time? Maybe they aren't as much, because I don't think we've really done that.
Well, we did. It really wasn't the military. We did. Several of the satellites we did bring back. I can't recall which ones were. Itelsat and Westar and Palapa.
Those were the ones
and we did retrieve those. And we retrieved those because they were. And it turns out, interestingly enough, they were insured by the by Lloyd's of London, and that was the biggest salvage operation Lloyd's of London ever achieved when they returned those satellites. Bigger than anything in the ocean they ever picked up. In fact, they rang the bell. When they have a big recovery, a big thing in Lloyd's of London, they ring a bell. And they came down to the Sir somebody, whoever he was, I don't recall who he was, but he was head of Lloyd's of London, came back, and we had a big reception at the Johnson Space Center after we retrieved Westar and Palapa. I don't think the Air Force really had that much demand at the time, or it went away, whatever it was, for retrieval and retrieving payloads. But commercials did.
What the military was interested in was the possibility of refueling satellites in orbit.
That's right. Yeah, we did do that.
When you have reconnaissance satellites, very often you have to change their orbit to get them over the right place at the right time. And orbital maneuvering fuel is a limiting commodity on satellites, and these are very expensive satellites to build. So if you have the possibility of refueling, then in principle you can extend the life of these very high value assets. And we did do a demonstration of, and of course the fuel in most cases is hydrazine, which is very nasty stuff. If you get it on your spacesuit, you can't come inside until you bake it off. And, I mean, it's fairly dangerous. And so we actually did do a demonstration just in the shuttle's cargo bay, but we've never actually done a real refueling of a satellite in orbit. But they're still working on it now. Now there's I think the military is still working on possibly robotic refueling technologies.
So for whatever the next version of the shuttle or crew vehicle would be, is it necessary or even really a good idea to have this huge cargo bay?
Well, I think that's what they're eliminating. I haven't been close to it, but
Yeah,
the CEV is going to be really a passenger carrier, and then any cargo will be on an unmanned vehicle, I believe.
Yeah.
So that's what they're separating is that right? I mean, I haven't been really that close to it.
Yeah, I mean, this is one of the guidelines now for future space vehicles is to the maximum extent possible separate humans and cargo. If the original concept of the shuttle had been realizable, that the shuttle would be capable of flying frequently enough that it could basically satisfy all of our launch needs, then you can make the argument, well, all right, you know, we're doing this and people are in it to fly it, and you know, we'll just do it that way. But given the fact that we can't fulfill that goal, then you have to ask, why put humans at risk just to take a satellite up in the cargo bay and launch it when we can launch satellites using unmanned vehicles? And in fact, that was the decision after the Challenger accident, was any payloads that are carried into space on the shuttle in general, I mean, there were some exceptions for various reasons, but you ought to be using the shuttle to do things where you need people to do them. And some of those things, for instance, the servicing of Hubble or the assembly of the space station, although even that could be argued that had we planned it differently, we might have been able to do it without making such extensive use of the shuttle. But there we do make full use of the big cargo bay. But future human space vehicles, the CEV, will be basically a people carrier with a small amount of cargo, and anytime you want to launch large amounts of cargo, you'll do it without people. Let's take a one or 2 minute break. I'm going to get my computer set up.
Yep.
And let me put this down here. I want to give you a short presentation just to bring everybody up to a certain level of familiarity with what the shuttle does and what it looks like. And again, I tend to look at this from an operational point of view. This will be informal, you know, ask questions as we go through. You know, as we've said, the two critical phases of shuttle operations and what makes this such a unique vehicle is it launches vertically like a spaceship with a tremendous amount of power, and it lands. You know, you look at this and you know, you have to remind yourself that you know, it looks like an airplane landing, and yet a half an hour ago this was a spaceship going in orbit around the Earth. So it really has been a spectacular technological achievement. Let's go through some of the maintenance operations, what is actually done to the shuttle. We've talked about it a little bit, but I think if you actually see some of the images, it will help to give some reality to some of this. So after the shuttle lands, here it's landing on the runway at the Kennedy Space Center, and as we mentioned, all of this is a bird sanctuary, and so sometimes you have to chase the birds away, and there's a problem from time to time with crosswinds. There's only one runway, so if you get wind blowing across the runway at more than 15 knots, you can't land, and so that's also a constraint sometimes to launch, because when you take off, you always have to be able to turn around and come back and land here, just like you have to be able to land over in Europe or Africa, and so there are a lot of launch constraints. What they do is was actually hooked up back on the runway, but they hook up air conditioning units They have to purge. There's an ammonia boiler. Remember we talked about getting rid of heat as you're coming in using water spray boilers. But once you get below 100,000 feet, the pressure is actually above the triple point of water, and you can't flash evaporate anymore. And so they switch from a water boiler to an ammonia boiler. And so after the shuttle lands, there's ammonia fumes all over the place. If you've looked at pictures of shuttle servicing on the runway, sometimes if there isn't actually a wind blowing, they bring around a big fan to blow the ammonia away, and everybody has to stay upwind of the ammonia. And there's also the possibility, of course, that there might be a hydrazine leak, or who knows. Anyway, the orbiter has to be safed, and you have the people come out in what looks like space suits, escape suits they call them, self-contained. I don't remember the acronym, but in any case, we're bringing the orbiter back to the hangar area, where it will undergo a lot more than 14 days of servicing. I remember, again, just to give you a sense of the state of mind before we were actually operating the shuttle. As a new astronaut back in 1978, and remember the shuttle didn't fly until '81, we were getting a series of lectures on all the shuttle systems, and I remember the lecture they gave us on turnaround, which was supposed to take 14 days. And we got a briefing from the people who were planning the turnaround, and I remember they told us, we've studied this really carefully, and we just don't think it's going to be possible to turn the shuttle around in 14 days. We've cut out every unnecessary step, and we think it's impossible to do it in less than 16 days. So, and that's kind of the way people were thinking. We were talking about, it's supposed to make 60 flights a year. And, people were skeptical. There's no way they can make more than 40 flights a year. People just didn't have a concept of how complex it was going to be to operate this vehicle, because it is such a complex vehicle. To operate it safely is difficult. Now, sometimes it lands in California, and in that case, you put it on the 747. This is the same bipod fitting that just to essentially duplicate the way that the orbiter is put on the external tank. And the tail pod is, of course, for aerodynamics. And that was also the configuration for the approach and landing tests. And actually later, and I think in the middle of October, Gordon Fullerton, who was one of NASA's premier test pilots, he still flies. I mean, he's still, I can't even, I'll have to find out from how many different types of airplane he's flown. He's just an amazing guy. But he was actually in the shuttle during that first approach and landing test, so he can tell us about what it was actually like test flying the shuttle, as well as being on the third orbital flight test. Yeah.
Do they carry anything on the airplane when they're taking?
You mean inside here? No, this is not your opportunity for a transcontinental vacation trip. There are a few. I mean, there are a few people who ride along with it because you need the maintenance people. They also have an airplane flying about 50 miles in front of this, checking for turbulence. And in the early days, they had a chase airplane as well.
That's when I told people they were crazy trying to get me to do this. That was the dumbest thing I ever heard of.
Okay. So now a look at some of the details. Remember we talk about how the engines are taken out. You get a little bit of a view here inside the engine compartment. I had the chance on numerous occasions to actually go inside the engine compartment, and I mean, it's just amazing. You get these huge big pipes, and it really helps when you're going to be using a system like this. We spend a lot of time in the simulators, and you'll flip a switch, and that switch controls what they call the main fuel shutoff valve. It's a big butterfly valve, about 17 inches in diameter, inside this huge pipe. And you sit in the simulator and you flick the switch, and the talkback shows that the thing is closed. And then you actually go in the compartment, and you look, and there's this huge pipe and this area in it, and you realize, you know, this huge thing that's moving around, and it kind of gives a sense of realism. And in fact, that's one of the big safety concerns. You know, when the fuel is flowing, the butterfly valve is in a vertical position, so the fuel flips by it. It's an unstable situation. If it goes out just a little bit, then the fuel flow can slam it closed, and you've got an explosion on your hands. So that was a major consideration. This is the body flap. So you can see all of the plumbing and all these red things are removed before flight stickers. It's a very, very complex process. And they pull the engines out after every flight now. And Yep, and that's the thing. You know, all of the platforms have to be designed so that they fold up and they fold down so that you can get access to all the places. I mean, it's a very complex system, and this was built. A lot of the equipment, the launch platforms and everything, as we mentioned, were adapted from the Apollo program, but the hangars, which we call the OPF, the Orbiter Processing Facility, was built specifically for the shuttle. The tiles we talked about, I mean, that's just a huge amount of work, replacing, maintaining, and testing the tiles. This is inside the cargo bay. You know, you've got the fuel cells, you've got hydrogen and oxygen cryogenic tanks, helium pressurization tanks, nitrogen for your atmospheric system. This is the bulkhead in front of which on one side you have the engine compartment, on the other side you have the crew compartment. And you know, like we mentioned, this has to be done essentially in clean room conditions, and yet it's on the scale of a battleship. So it's a real challenge. This is the forward window. On, you know, maybe 1 in every 5 flights we'll get a little ding on the windshield from a little piece of usually orbital debris. In fact, more often than not, it turns out to be little paint chips. On one of my flights, whenever they do that, they remove the window, they replace it, and they do a chemical analysis to see whether it was a micrometeorite or a piece of space debris. The windows are actually, there's 3 panes. There's a redundant pressure pane. There's the 2 panes on the inside are capable of holding pressure, and the outer is a thermal pane. This is one of the orbital maneuvering system pods. These are removable because, again, they contain nitrogen tetroxide and hydrazine. And we mentioned the fact that these are called hypergolic fuels. When you bring them together, they ignite spontaneously. As opposed to hydrogen and oxygen, you need a spark igniter. So they're in that one sense, it's a nice system, because when you want to use them in your reaction control and you only want to say, you know, a very tiny 1/10 of a second pulse, you don't have to worry about an igniter, which is a potential failure point. You just squirt in the hydrazine and the nitrogen tetroxide, and but they're very nasty stuff. They are extremely toxic, and of course highly combustible, and they're very corrosive. So these pods are serviced in a place far away from where the other activities take place for the orbiter. So just in case there's a leak or an explosion, it's not going to take down the rest of the critical facilities. So this is the orbiter maneuvering engine. And then they also have the smaller reaction control engines. And there's 2 aft pods, and all the fuel tanks with the hydrazine and nitrogen tetroxide are in here. The aft system, the 2 pods, they actually have interconnects so that you can actually cross-feed from one system to the other, and all that stuff has to be hooked up. The forward system is independent. You can't cross-feed to that. The landing gears, we talked a little bit the other day about the tires. You know, these things sit up in space for 2 weeks at a time. You've got to worry about thermal control. You've got a, you know, can you imagine if you had a slow leak and, you know, you found out that your tire was flat before you started your reentry? So, and then, of course, the problem of sealing this against the hot gas. You know, the tiles on the edge of the doors for the landing gear, that's a very critical section. Anyway, after typically about a 3-month turnaround in the hangar, they wheel the orbiter. Actually, originally it was pulled over on its own wheels, and then but that required that they then stow the wheels in this big vertical assembly building. This is the vertical assembly building. Hopefully you've seen pictures, I mean, of it. It's huge. It was actually built to assemble the Saturn rockets. It's much taller than we need for the orbiter stack, but it has been adapted. So what goes on here is it's wheeled into the big vertical assembly building. In the meantime, there it is, actually on the inside. You just don't get a sense of the size of this building from any picture that can be taken. You have to be there and see it to really appreciate it. Okay, in the meantime, you remember the solid rocket boosters are recovered after every flight. And the Liberty Star and I think the Freedom Star, that's the NASA Navy. These boats are positioned out offshore, and they have divers, and they go down and they put in plugs and flotation devices so that they actually float the boosters, and they drag them back where they're disassembled, cleaned up. The actual segments which contain the fuel are shipped back to Utah, to Thiokol, which is now ATK, for cleaning, refilling, and the other parts, the nozzle and the top, which contains the electronics and the parachutes, those are serviced in Florida. And then they're brought in segments into the vehicle assembly building, where they are stacked. And remember, those are the segment sizes that some of these are assembled in the factory. Those are the so-called factory joints. And then where these are come together, that's the so-called field joint, and that's the joint that failed in the Challenger accident. This gives you a sense of the size of those solid rocket motors and the way the solid fuel is put in. And they do all of these tests to look for the roundness of the motor and the flatness of the propellant. Yeah.
Is that the fuel itself that you're seeing?
I think it's, yeah, it is. Although what confuses me about this is I'm not sure which segment this is, because most of the fuel is actually put in with a star pattern in it and they actually shape the way it's loaded so that you shape the thrust profile. And I've not been able to get a good explanation of why that is not the case here. In any case, this is now the process where they lift one segment, they put it down on top of another. Of course, all of these are hazardous activities. Nobody is allowed, except for the critical personnel. Nobody's allowed in the VAB when they're doing this, just in case there's a problem. And then they actually put all of these bolts in to join up the field joint. And now, of course, after Challenger, we have a new and improved O-ring configuration. Wow. Okay, so now we have the two solid rocket boosters sitting on the mobile launch platform. And again, you can see you have to design all of these platforms so you have access, and it's... Now, the external tank we talked about, this is in Michoud. This has actually been damaged, not too heavily, but it did suffer damage from Katrina. So this is the oxygen tank up front. Notice how small this is compared to this is the big hydrogen tank. and then this is actually the front side, but this is then turned around, and the two are joined together inside the outer shell. And of course, the external tank is what the solids are joined to the external tank, the orbiter is joined to the external tank. So basically, the external tank needs a strong back mechanism inside it, because that's ultimately what's tying the whole stack together. And the thrust from the solids and the thrust from the main engines, ultimately they're linked together through the external tank. So the tanks themselves, the hydrogen and oxygen tanks, don't have a lot of beefy structure, but going through this is a very heavy structure to yeah.
Hydrogen tank there is about the diameter of the overall structure.
Yeah, yeah, yeah. That gives another idea of the scale. This is cleaning and polishing inside the big hydrogen tank. I mean, it's again the scale of all of this is it's important to get a sense of what's involved in taking care of these vehicles.
People actually have to go in and strip it by hand?
I guess. I mean, you because the scrubbing is only part of it. The inspection is the really critical thing to see if there's any, anything that's not quite right. Sure.
One thing that's interesting, the use of liquid oxygen, liquid hydrogen, is wanted so much because of its high performance. But on the other hand, if you would do something like liquid oxygen and kerosene, you would get a much smaller tank, or some of the propellant. And there is a trade-off, I think, today people are realizing, especially from the Russians. The Russians don't really use liquid hydrogen that much. You get a lower ISP, but your tanks become so much smaller to deal with. And hydrogen's very hard to deal with. It's very hard to find a hydrogen base. And hydrogen is very hard to deal with.
My second flight, you remember that was the one with the hydrogen leaks. Remember that? We went down. We were supposed to launch in May of 1990. And we went down, and when they before they fill the system, they do a helium leak check. And of course, helium, for those of you who have worked with vacuum system, helium will leak through anything. And if the system is tight against helium, they figure the problem is that that's done at ambient temperature. And when you fill it with the cryogenic hydrogen, everything contracts, and so things which were vacuum tight at ambient temperature are not always vacuum tight. And in fact, but the problem is you don't know that until you fill it, which is only done, a few hours before launch. So, we had gone down to the Cape. We were in medical quarantine, and we just got the message about 6 hours before launch. There's a hydrogen leak. Launch is scrubbed. They did some checks. They drained the tank. They did another helium leak check. It was fine. We had gone back to Houston. We came back. Same thing happened. Well, in the end, we made 6 trips over the course of 6 months. We didn't launch until December. And actually, another one of the shuttles also had a hydrogen leak. When they actually alternated us, they pulled us off the launch pad. They put somebody else on. I mean, it was just what had happened was they had somewhat changed the procedure of installing some O-rings in these big hydrogen lines, and it required a process where the workers were actually working in an area where they couldn't see, and the O-rings were being installed slightly wrong, but it was just terribly difficult to track that down. So yeah, there's a lot of problems using cryogenic fuel. Now, the other thing is, if you have a fully staged vehicle with a separate first and second stage, one of the things that you learn in rocket propulsion classes is that in the first stage, the specific impulse is not nearly as important. What's really important is to get a lot of thrust. In your upper stages, having a high ISP becomes much more important in terms of the payload that you can carry. So if you had a fully staged vehicle, And that was in fact, that's the way Saturn worked. The first stage of Saturn was kerosene and liquid oxygen, and the upper stages were cryogenic with hydrogen and oxygen, just for that reason. Okay, let's move on. So now we have the external tank, again, suspended in the vertical assembly building. That's lifted up and joined between the two SRBs. This is the feed line where the oxygen comes down, and this is where these two are the feed lines. This is the hydrogen, and then the orbiter has two corresponding feed ports where the hydrogen and oxygen comes into the engine. And actually, when you fill the tank on the pad, you actually put the hydrogen and oxygen into the orbiter, and it flows from the orbiter back then into the external tank. And it was on this oxygen fitting from the foam that they put around this was what fell off in the recent Discovery flight, where they did get a big piece of foam. Okay, so now we go back. Remember, we brought the orbiter over into the vertical assembly building. Now you put this strong back to hold the orbiter, and this is really spectacular. I mean, you lift the whole orbiter up off the ground, and you tilt it up, and then you basically hang it and lower it. And you know, this is you know, these are big pieces of equipment, and yet, you know, you need millimeters of accuracy. So you have very skilled crane operators, to say the least. Okay, so now we have the orbiter, and the strong back is laid down in position, and all of the mating is done. And we're on the pad, excuse me, we're on the mobile launch platform, and they put the crawler transporter underneath it, and then they roll it on these specially prepared paths, which have very, you know, I don't know how deep it goes into the ground, but this is heavy river gravel. Most of the boulders are about the size of your fist, but after one or two trips of the orbiter, it's crushed down to the size of pea gravel, and then they have to replace it with new stuff. And of course, as you're going out to the pad, when you're rolling up to the launch pad, you're actually going up at an angle. And so this whole system, you can see the crawlers down here. Each one of these treads, each single piece of the tread weighs a ton. I mean, just to give you a sense of, it goes about 1 or 2 miles an hour top speed. It takes hours to get out there, and it has to be capable of staying level to within a few degrees, even as you're climbing the ramp up to the launch platform.
So what's supporting, what are those things supporting
These are, the whole stack is basically sitting on the two SRBs. The skirts of the SRBs is taking the weight. These are the fuel inputs, which are connected through the other side, where the hydrogen and the oxygen run into the shuttle, and from there, in the way I showed you before, it goes into the external tank.
They also keep it tilting back? Does it have a tendency to,
on each of the SRBs has 4 bolts. I'll bring in, I have, they give us as a souvenir after a flight, they give us the big nuts that are explosive bolts. So there's 8, 4 on each of the SRBs, and that's essentially that's what gives it its stability. Okay, so, you know, again, we have to, this is a hill. It's a little hard to see the perspective, but keeping the whole thing steady. And we talked about how you can see this track here where the payload changeout room eventually can come around and cover the shuttle to give it protection. Yeah, this is actually going up the hill to get up, and it's just a pretty picture that I like. And here we are. This is nice because you have both shuttles on the launch pad. This is a big water tower. In order to protect the launch pad against flame damage, and also to protect the shuttle against acoustic effects. They actually get a shock wave when you ignite the engines, which can bounce back and do some damage. So they shortly, about 15 seconds before T0, they open up the valves, and all that water flows with little jets coming. If you've seen pictures of launch, sometimes they show that as part of the launch sequence. In fact, in another class, I'll show you some of the details of an actual launch picture. So that's the water deluge, and that goes for about 30 seconds, and that cushions the acoustic load reflected back to the shuttle. Okay, that's enough pictures on the pad. Oh, I know what I wanted to show. This is called the White Room, and that's how the crew goes in. You take an elevator up to here, and then that actually joins up with the hatch. So the hatch is sitting open, and you put on your parachutes and the last few pieces of equipment to get in. And this is a view inside the White Room. This is, I guess, from our last flight in 1996. So, and when you go out on launch day, the big thing that you notice that's different is there's very few people on the pad, only the essential personnel, and the whole stack is creaking because it's now filled with the cryogens and everything is shrunk, and it's alive in a very strange way. So we talked about the mission profile. I won't deal with this, and I think I do want to talk about some of the shuttle aborts, but we'll do that another time because I want to get finished with the slides. I did want to show you, after Challenger, they introduced a bailout. We did mention that the basic survivability for the crew requires an intact orbiter. It used to be that it needed an intact orbiter landing on the ground or ditching in the ocean, which was kind of an unlikely survivability because you're going to hit the ocean at 200 knots and probably break up. So now there are circumstances where you can lose more than one engine during launch, or you might have to do an emergency deorbit where you basically can be flying along at 40,000 feet stably, but with no place to land. And so that's really the only situation which the bailout system protects you against. But there's a collapsible pole. The reason for that is because the aerodynamic studies show that if you just jumped out of the open hatch with a parachute, the airflow would carry you back on top of the wing, and you'd hit the ohms pod, and that would not be a good deal. So you actually hook yourself to this escape pole, and that takes you down below the wing, and then you can open your parachute. That's and we actually practice this where you go out into a swimming pool using the escape pole. These are some actual tests conducted by Army parachutists in I think it was a 141 transport. So the system has been tested in flight, although never with a shuttle, and that's the test where they have us do this. They have a simulated hatch, and you basically jump out into the swimming pool. So once again, into the White Room, you can see the hatch out here, and that's the last thing that they'll do is they close the hatch, then they pressurize the shuttle by about 1.5 psi just to make sure that it has pressure integrity before launch, and then we launch. As you can see, you're burning hydrogen and oxygen in the main engines, so what's coming out there is just hot steam, not very visible. Most of the smoke and the noise and everything comes from the solid rocket boosters. However, you do need these engines. In fact, the people have calculated that if you tried to take off without these main engines pushing up on the shuttle, that the attachment between the shuttle and the external tank would probably fail. Each of the main engines is about, well, it's 500,000 pounds of thrust in vacuum. It's slightly under 400,000 pounds at sea level. So you've got, a little over 1 million pounds coming from the main engines, but these are putting out, almost 3 million pounds apiece. So most of your early thrust in the first 2 minutes are coming from the solid rocket boosters. And it's a pretty rough ride. I mean, there's a lot of vibration. When you go through Mach 1, which is max Q, maximum dynamic pressure, the vibrations are even more pronounced. In fact, the first time on my first flight, I really thought the wings were going to come off. There was so much vibration, but of course they don't. But I'd love to get a hold of it. I actually saw a high-speed, slow motion picture actually looking at the tail as you go through max Q, and you can actually see the tail fluttering back and forth like that. I mean, the loads, the aerodynamic loads on the vehicle during ascent are significant, and you do actually have to move your elevons to, it's called load relief, in order to take stress off that. So this, I really like this. It gives a sense of the power that you're sitting on top of to get up there. And that's just a nice picture of riding the fire. Okay, so you get up in orbit, you drop the external tank, and although now they're going out of their way to take even better close-ups of the tank to look at the foam shedding, we've been doing that, in fact, throughout the history. Now they specially time the launch so that you're guaranteed to drop the external tank with good lighting conditions. That didn't used to be a constraint to launch, but it is now. You can also, by the way, see how the atmosphere quickly fades out into space. And that's a telephoto, so it actually makes the atmosphere look even thicker than it really looks when you... Okay, so there's the orbiter in space. That was actually after it had delivered a payload. This was taken from the space station. And just a quick reminder of all the different things that we've used the orbiter for. Launching satellites, you've seen that picture. This is a payload assist module to take the satellite from the shuttle orbit up to geosynchronous transfer orbit. We have used it extensively for satellite repair in orbit. This is the Intelsat, where it was put into orbit by an expendable rocket, but into a bad orbit because of underperformance, and they managed to get it into a shuttle-compatible orbit. And I won't go through the whole history. That, why there happened to be 3 people out there is a whole story in itself. This is one of the satellites that we actually, again, the satellites were put into orbit by the shuttle, and the shuttle deployment was fine, but the payload assist module, which you saw before, did not perform properly, and so the 2 satellites were stranded in a useless orbit. We went back and we actually brought them back to the ground. They were refurbished and relaunched again on expendable rockets. The shuttle has also been used as a space station with the space lab on the inside. So, to carry out scientific experiments. This is a large pressurized module which is put into the cargo bay. And the original idea, as Professor Cohn mentioned, was you could just take your laboratory equipment off the shelf, plug it in here, 120 volts AC power, I guess, and it would be just like working on the ground. Well, it never was, but having said that, I think the Space Lab program as a whole was extremely successful. And then it's been used to service the Mir space station. We certainly added several years of useful life to the Mir station because we could carry up a lot more equipment than the Russians could themselves, and that was also gave us an opportunity to get some U.S. astronauts on long-duration space missions. And then, as you all know, we're using the shuttle to construct the International Space Station, and hopefully we'll get more of it built before too long. The shuttle is also an excellent platform for performing EVAs, spacewalks. And that's a picture of when we went up and repaired the Hubble Space Telescope. I can't overestimate the capability that the shuttle gives us as a work platform in orbit. We can do this sort of complex EVA activity on the space station, but once we retire the shuttle, we've essentially lost that capability. You know, to have the manipulator arm as and to be able to use people, and the robotic arm to move equipment around. It's just a very powerful work platform. That's one of my favorite pictures, just floating up there.
Walt Guy is an expert on space. He's also responsible for space design, so I'm going to ask you some questions.
So this is a pretty picture of firing the orbiter maneuvering engines just to start your descent into the atmosphere. You know, despite the fact that you're going at 18,000 miles an hour, you only have to slow down by a few hundred feet per second in order to lower your perigee down to essentially the surface of the Earth, so that half an orbit later you intersect with the atmosphere. And of course, that produces the aerodynamic heating, which you can see on the outside. This is looking out to the front. That's kind of a dull glow. You know, it starts out as a deep red, and then it gets orange and yellow, and finally white on the outside. The most spectacular thing, you know, you're a meteor. So this is a picture that was taken from Houston, looking at this is at about 250,000 feet at about Mach 12 on the way to a landing at the Kennedy Space Center. And on the inside, if you actually, shuttle is flying like this. So if you look up the overhead windows, you can actually look back into the wake. And this is really spectacular, because you have these different colors, and it's sort of shimmering around. And every once in a while, when I would be looking at this, you'd see a big bright light going, you know, and I would think, boy, I hope that was nothing important. It was probably what people said it probably was little bits of gap fillers. You may have heard that on the last flight they discovered that some gap fillers were protruding, and so Steve Robinson went around and actually pulled some of them out. But they've probably been doing that the whole time, and they just come off. And it's really this little point where you have the convergence of the shock waves. This is about 10,000 degrees Fahrenheit, so that's the surface temperature of the sun. It's a spectacular visual view, and then again, at this point we're just going subsonic, flying like a glider, and ready for touchdown. So I hope that gives you some sense of, you know, visually what goes on in the course of a shuttle flight, with an emphasis on the maintenance operations. You know, without appreciating how complex it is to operate this system, you know, I think it's hard to really make the link between the original concept and the difficulties we've had in getting the shuttle to perform in terms of the turnaround and maintainability. So again, just wrapping up, that's my kind of farewell picture. But the shuttle, it was an amazingly ambitious concept, and I think what has been astounding is how well the shuttle has been able to perform and do all the things that it was designed to do in terms of the satellite launching and being used as a science platform, performing EVA, repairing satellites, building space stations. You know, it's given us experience and capability to learn how to do things in Earth orbit, which we never had before. And as I say, we may well miss them once we retire the shuttle. But where we really did get it wrong, and this will be one of the things that we'll look at when we deal with the individual subsystems, is in the operations. It turned out to be a lot more complex, expensive, and delicate to operate than had been anticipated. And so hopefully there will come a time when we set out to design another reusable vehicle, possibly a reusable winged vehicle, and I think a lot of what we've learned from the shuttle will be folded into that. It still is a question of how reusable the next crew exploration vehicle, the CEV, will be. Reusability has been put in as a requirement, but that remains to be seen. And certainly the experience that we've gotten from the shuttle is going to make people look really, really closely at what assumptions we're making about the reusability whenever we do this again. Okay, next Tuesday will be the last in kind of the conceptual part of what we're doing. Professor John Logsdon from George Washington University is a very well-known space policy analyst. He did a seminal study on the Apollo program and has also written a lot and done a lot of research on the origins of the shuttle, and so he'll talk to us then. So let's see, I had promised to post everybody's emails on the web, and I got diverted and didn't get that done, but I will do that before tomorrow. So, you know, in terms of forming your teams, put together an idea of what system you would like to work at. If you're not able to form up as part of the team between now and Tuesday, just give me what your own personal preference is, and then we can look at it and see if, you know, if different people are interested in the same system. You know, we'll let you all know and help you form up teams. Yes. Yeah, I think your email is I'll make sure that it's in there in the student view. Okay? Yeah.
For next week, the paragraph and preferences.
Yeah, I just want to know what.
As a group or turn in individually?
Well, I mean, if you've already formed a group, then just turn in something as a group. That's fine. If not, if you haven't hooked up with somebody, just you know, let us know what system you're interested in working at and any ideas you might have of what you're going to look at. You know, really, this is just a very, very short write-up, essentially to get you started. Okay, and if you that way, if you have any questions, we can talk about it next Tuesday.